I want to do this today because I'm finally there, and it's calculus. Finally, well, we limits, right? Limits is calculus, but we finally get what this stuff means in calculus, what a vector function is, calculus-wise. So here's the derivative. Here's the definition of what a derivative is. Here it is. Derivatives look like this. F prime of x is this limit one way you can write it. Some people have the h there. I know I teach it that way. That's definition derivative. Literally, it says this is rise, this is run. Difference in the heights, difference in the x's, rise over run. If you let the distance approach 0 between these two x values, the distance between the points is so close that we define it to be the slope of a curve at a point, or the slope of a tangent line to a curve at a point. We say that this is the derivative. That's what that is. Basically, it's saying, hey, take 2 points, make them really, 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 really close, so that there's like virtually no difference between them. Is there a difference? Yes, but it's smaller than anything you can imagine. It's microscopically small to the billionth power. I don't even know how to say it. It's so small that there's essentially no difference. Is there a difference? Yeah, but you can't put a number on it. So that we say that we define it to be the slope of a curve at one point, even though there's 2 little points. We define it that way because it's infinitesimal. There's no difference between it. We're going to use this right now. We're going to talk about what the derivative of a vector function means. So let's take that vector function and let's talk about a derivative. Well, it's still going to be a limit, but x is not the only thing changing. The independent variable is what is going to be approaching 0. So we say, okay, well, then this would be a vector function where we have a difference in 2 vector functions, and then we allow that difference between them to go to 0. Here's what I want you to know. This thing does exactly the same thing as this thing. Only it does it with a vector that is tangent to a space curve. So this right here gives you a tangent vector. This gives you a tangent slope. Slope of the tangent line. Does that make sense? This gives you the tangent vector to a space curve. It gives you a tangent vector. It gives you a tangent direction. Just like slope, we don't have slope. We have vectors. That gives you a tangent. So this is defined to be the tangent vector to a space curve, the curve that we're talking about. Curve through space, vector function, whatever you want to say, that's what it is. We're finding tangents. I want to tell you this is interpreted to be a couple things. Firstly, the tangent vector. But secondly, this is also interpreted to be just like that as instantaneous rate of change. You remember that? Slope. Slope of a curve at a point. Yay, that's what it is. Or instantaneous rate of change. Yeah, it's fantastic. Or velocity, instantaneous velocity. That's also what this is. This is also instantaneous velocity of a particle moving through space. A vector has a direction, yes, but also has a magnitude. It's telling you how fast it's going and in what direction at a moment of time. It's also interpreted to be instantaneous velocity. Now, I want to show you how it works. I want to prove that this actually makes sense. We're going to end with. We're not going to have time for example. We'll do it next time. But I want to give it to you at least what it looks like. Imagine, if you will, just this space curve, vector function just through space. And I want to find the tangent vector to that point on that curve. Can you understand that I can't just find the slope? Because slope doesn't really make sense when we're going through space. I've got to find out what direction vector? Because this curve is coming all out here, right? So what vector is perfectly tangent to that thing? What direction is it headed in? What's its instantaneous velocity? What's its heading and the speed that we're heading there? Does that make sense to you? I need a vector to do that. So the idea behind it is, let's take P and Q, like we normally would in Calc 1, and what I'm going to do is allow these points to get really, really close. Only vector functions do this. They point places, right? This vector is what we think of as R of t. It's that vector pointing to the point that I want. This one would be that t plus a little bit, just a little bit more time. It says, hey, this is the point I want to find my tangent vector at. This is the point that I'm going to let get really close to p. So what we do is we say, let's let this time distance, this guy, delta t, let's let that go to 0. Then what's going to happen is that this vector, please look, this vector is going to start getting really close to this vector. Does that make sense? How close? Really, really close. Really, really, really close. How close is that? So close that it makes really no virtual difference. Is there a difference? Yes, but it's infinitesimally small. Therefore, this vector that we attach to these guys, go, yeah, let's put that vector here. The secant vector, if you will. When I let this get really, really close, the secant vector starts becoming very close to the tangent vector. That is what is going on here. So when I take this, hey, here's a vector from origin to Q. This one here is vector from here to here. I'm finding the vector between them. And then I allow this distance to go to 0. It's moving this vector, moving it really, really, really close. Really, 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 really close. And as soon as we get there, we're not actually there, right? That's what limit does. It moves it really close so there's no difference. Then we have something that looks just like. Is it exactly? No, but we say yes, define it to be the tangent vector. That's what we do. How? Because the limit allows it to be so close to 0 there's virtually no difference. Chopin's you understand the concept here. So here's the whole proof. So this thing is defined to be the tangent. If you want to see the proof, which you all do, of course, here you go. Look, here's the proof. It's very easy. If we take this, here's what vector functions really are. A vector function is simply the x component, the y component, and the z component this right here, I want you to see it. This is this vector function. It's f, hey, same stuff inside, f, g, and h. But if I do this, this is this vector function, f, g, and h. There's only t's in here. There's t plus h's in here, and delta t. But here's the beautiful thing about it, and this is our whole punchline. Here's the beautiful thing about it. If I take this minus, let it distribute through, and recombine this, watch carefully because I don't want to lose you here. I can take this f of t and this f of t plus delta t. They both have i's. I can jam those together. Do you guys see what I'm talking about? I can jam them together. So this limit becomes I want to do it once because I'm running out of time and I don't really want to write just ad nauseum here. Do you understand that I can do these two things? I can group my F's, my G's, and my H's, and I can also break them into 3 fractions, each of which has the same denominator of delta t. Head nod if you understand that. So I'm going to put, hey, stuff with F's, I, some craps with G stuff, J, and some crap with H stuff, K, and they all have the same denominator. Do you guys see what I'm talking about? It's going to look the same. It's just this has G's and this has H's. But here's the cool thing about limits. Limits are separable by addition. Limits are separable by addition, which means that the limit of this guy, man, I freaking hope that you're watching right now. The limit of this guy, limit of this guy, limit of this guy. But look at this guy. This is exactly the same as that. It's exactly. And this would be exactly the same with some G's. And this would be exactly the same with some H's. If it's exactly the same, then by definition, so this is the same as this. This has to be f prime of t I. Did you guys catch it? The limit of this has to be g prime of t with the j. We got the j's from here and here. We grouped our i's, there's the I. We grouped our j's, there's the j. We grouped our k's, there's the k. We had our f's in the same spot because they're f components, g's in the same spot, they're g's components, and then h in the same spot, there's h components. And this is the definition of a derivative of a function with respect to t, and then g, and then h. And this is what we came up with. If this is the definition of a derivative, and these are the definitions of vector functions, and we regroup them, i's, j's, and k's, and we separate these limits by addition, which is perfectly fine to do as long as delta t is going to 0, then this is the definition of a derivative of f. And this would be the definition of derivative of g. And this is the definition of derivative of h. Then this is the definition of a derivative of a vector function. And you go, wait a minute, is it really that easy? Yes, it really is that easy. Take a derivative of each component, and you have the derivative of the vector function, and that is it. Test time, I guess. So, welcome back to 12.2. What we learned last time was the proof of the thing that I'm going to write here. The thing that I'm going to write here is how we take derivatives of any vector function ever. And it's, man, I hope it's intuitive for you, but if it's not, it's really easy to take derivatives of vector functions. It's this. The derivative of a vector function, if it's x component I, y component j, h component k, and they're all in terms of t. Remember that parameter is basically parametric. How we take derivatives is literally just piece by piece. So the derivative of a vector function is the derivative of the x component, the derivative of the y component, the derivative of the z component, and that's it. That's literally all there is to it. So what we're going to do today, we're going to practice, maybe 3 examples of this, just the derivative, and then I want to move on. I want to move on to what we can actually do with it. So we'll start talking about, well, in Calc 1, you got stuff like tangent lines, right, for curves. Well, this is Calc 3. We should have tangent lines for curves, and vector functions are curves. So we'll figure out how in the world we're going to make a tangent to a curve at a point, just like we did in Calc 1, which is a pretty cool idea. So let's start with some simple derivatives. We'll get a taste for it. Then we'll get on into how you make tangent lines. And then we'll talk about integration. Like, how can we go backwards? So let's give it a try. Do y'all feel confident that you're able to take a derivative of this thing right now? If we're talking about with respect to t, can you do it? Yeah. Pretty sure we can do that, yeah. Because we can separate derivatives by addition, subtraction, it makes it really nice. So let's take the derivative. Everybody in class right now, tell me the derivative of t with respect to t. 1, and then we have what? How about the next one? What are we going to get? 2t. And last one, please. 3t. Good, don't forget the squared. Okay. Now, the interpretation. What is this thing? Well, when I did the proof last time, what we learned is that the derivative of a vector function gives us, just like the derivative of a function, gives us the slope of the tangent line to a curve at a point. We lose the idea of slope in 3 dimensions unless we're restricted to a plane. We'll talk about slope on directional derivatives. We'll talk about that stuff in a later chapter. But we kind of lose that idea. So what I want you to interpret this is, what the derivative of the vector, don't forget that, I always forget that stupid little apostrophe too, for a derivative, but don't forget that because we actually did something, was a derivative. What the derivative of a vector function is the tangent vector to a curve at a point, not just the slope of the tangent line. Well, here we have direction of a tangent line. Remember how tangent lines have direction vectors. Are you understand what I'm talking about? We are literally finding the direction vector for the tangent line to a curve at a point. That's what this is. Direction vector of tangent line. To what? We always get wrapped up in calculus, just doing calculus and forgetting what we're actually doing. If we got a derivative, we got something that is a tangent. In this case, it's a tangent vector. It's a vector that is the direction vector of a tangent line. But to what?
A curve on a circle.
What curve?
On a circle.
That curve. That right there is a vector function. It's a curve through space. It's called a space curve. Some of you guys said that. But it's to that vector function. So a direction vector of the tangent line to the space curve at any point. But any point changes a little bit because look, what's our only independent variable that we have here? T. So it's really kind of at a time, at a point, but the point is t. At any t for our vector function r. That's really what we're doing here. So whenever I give you a vector function, say find a derivative, what is, in your own words, what are we finding? If I say find the derivative, what's it mean?
Slope of the tangent line.
Okay, it'd be slope if we were only in 2D. In 3D, we change it just slightly because we don't have slope. We have direction vector of tangent line to a curve at a point. In Calc 1, it's slope of a curve at a point, or slope of the tangent line, which is really what it is. Slope of the tangent line to a curve at a point. Here it's direction vector of the tangent line to the curve at the point. Should parents feel okay with that interpretation of it? That's what we're doing. Now before in Calc 1 we could do like second derivatives. Can we still do that? Yeah, we can still do it. Let's find another derivative. It's done exactly the same way. What would you do here? What's the derivative of I? What is that?
Zero.
Zero, just like any other constant. That would be a constant here. So we have what, please?
2j plus 16k.
Now we're going to talk more specifically about acceleration and velocity later on. For right now, I'm just going to leave it that we can take second derivatives and they're done exactly the same way as we would do anything else. We'll talk about like unit tangents today. We'll talk about that at the end of our lesson. We'll talk about unit tangents, what those things mean. But when we talk about acceleration, we have some specifics I want to cover later on. So right now, if I just give you a basic vector function, can you find the derivative of it? Can you find the second derivative of it?
Yeah.
Can you prove it to me right now? I'm going to give you one example. I want you to find the first two derivatives. Okay, there you go. Firstly, is it a vector function?
Yes.
Yep.
Yeah, it's got I, J, and K. There's some T's up there. So this describes some curve through space. Do I know what it looks like? No. But what's awesome about it is even if I don't know what it looks like, I can still find the formula, it's called that function, the derivative that gives me the direction of the tangent line at any point to that curve. So I want you to find the first two derivatives, please. By the way, don't just wait for me when I ask you to do that. This is the only form of guided practice I can do in this lecture hall type setting. Really try it. It's a risk-free environment for you to get this wrong right now. So even if you get it wrong, that's okay. But at least try it. Don't just sit there passively. So vector functions, yeah, they give us space curves. The calculus of vector functions is really nice. Just like a first derivative gives us a slope of a curve at a point in 2 dimensions, this gives us the slope, but it's a direction vector of a space curve at any point. That's what we were finding at any point t. Did you find the first derivative at least?
Yeah.
Left-siders, you guys only. What's the first derivative here? Can you tell me?
1/root t.
1/2 t minus 1/2 t to the negative 1.
Could you do it both ways? You can leave. You know what? If I know I'm taking a second derivative, I'm probably leaving this like that 1/2 t to the negative 1/2, because the second derivative is going to be based on that. And you can do the same thing here. If you want to leave that as t to the negative 2, that's probably a better idea unless you're really good at doing them in your head, that's fine. And then 1/t, you can leave that as t to the negative 1. Either way is fine. Now, if I'm given a final answer, like, well, what's the final answer? Whatever I give you here, like if I give you a square root, I want your answer in terms of that square root. If I give you the 1/t, I want your answer in terms of that 1/t squared. Just put it back in the format that I give it to you, and that's generally accepted. So that looks pretty good to me. I need a show of hands if you got that. You got at least one of those two things, yes or no? Perfect. Let's keep going. Notice, probably wouldn't use this format to keep on going with the second derivative. Probably would use this one. So our second derivative gives us
Negative 1/4 t to the 3/2.
plus or minus?
Plus.
Plus. Because if you have this as, and this is probably one of the reasons why you leave this, if you're one of those people like I am, honestly I am, I make a lot of sign errors if I don't write stuff down. I really do. So I would probably personally leave this as t to the negative 2 right now, because I know that when I bring down that negative, I'm going to get negative, negative, positive. Does that make sense? I'm that guy. And I'd probably leave this one as t to the negative 1. Just because when we see it, when we see that sign, it's a lot better practice for us to see that on paper rather than have to make it in our head. Does that make sense to you? Even though we're in Calculus 3, you know this, right? Sign errors happen to us all the time. So the more practice we can get with writing stuff out appropriately, the less sign errors I'm going to have you make. So here, negative times positive, okay, negative 1/4, subtract 1. Here I know I'm going to get plus 2 t to the,
Negative.
and then,
Minus.
oh, before that.
Oh.
Yeah, don't forget those pieces, all right? That means that we still have this vector here. Remember that we're finding the direction vector, not just some scalar function of t. We're finding a vector function still. And then lastly, minus plus. Come on, quickly.
Minus t to the negative 2.
Okay. I want to show of hands if you feel okay with at least that one. On a test, would that be the correct format that I would want back from you?
No.
Probably not. I want you to put it back like this for 2 reasons. First, that's how I gave it to you. And secondly, it's easier to plug in numbers to stuff like this than it is to stuff like this. Because you got negative exponents floating everywhere. That's crazy. So if we, yeah, I'm right, Willow. If we write this back, the second derivative with respect to t is Oh man, what would that be?
Negative 1 over 4 t, I guess.
T, square root of t.
You could do that. You could simplify it if you want to. You can leave it as a square root of t cubed. You could do that. If you want to simplify that to t square root of t, like Corey said, that's fine also. Either way. Don't forget the I though. Plus 2 over t cubed j minus 1 over t squared k. Listen, I know it's not super hard, but I need to make sure I'm actually explaining it well enough for you. Am I? Do you understand how to get those things?
Yes.
Now, what is it? What is this first derivative? What's the interpretation there? What is that thing?
The direction vector.
Good. Direction vector of what?
A tangent line.
Tangent line to?
It's basically
Perfect. That's what it is. Instead of slope of a curve at a point, we have tangent vector. Direction of the tangent line to a curve at a point. That's it. Now, you know what? We get a lot harder derivatives. These are probably the two easiest ones that you're ever going to get. When you start getting like harder derivatives, please feel free to do the derivatives individually. That's the way I would do it. Let's try a couple of those and then move forward. You know I'm going to make you practice trigonometry, right? You know that. You know that, right? Because I'm the Leonard. That's what the Leonard does. Talks in the third person and does trigonometry. Yeah.
You've been talking to Rick, haven't you?
Who?
Rick. Big on trig.
Big on trig rig.
Just big rig.
The big rig.
Yep.
I know. It's pretty cool. The big Leonard just doesn't have the same. Weird. Look, this is. You can do it in your head. You can, it's possible. But it might be a really good idea to just take the derivative piece by piece because you know what? When we do things in our head and we try to go really fast, we make really stupid mistakes. I do. Do you?
Yeah.
I do the same. And I go, oh yeah, I just want to do negative e to the negative t cosine t because I'm just taking derivatives of each little piece that are multiplied together with t's in them.
Product rule.
I start drinking at night because you make those mistakes. Thank you very much. Don't do that to me. Don't make me drink at night. Watch carefully for these things, and the slower, be efficient with it. Don't spend 30 minutes on the problem, but maybe separate these out and go, okay, you know what? If this is my x component or my f of t component, let's find f prime of t. Let's do that separately. Just focus on this piece right now. Focus our mind on that, and then deal with the next one, deal with the next one, and then put it back together. Does that make sense to you? So here, now I don't care how fast or slow you do this. Just give yourself enough time. Separate it out and focus on that piece rather than the whole thing at once. If you're really good at product rule and chain rule, go for it. Me personally, I'd go, okay, derivative of the first, I know chain rule says negative e to the negative t. Derivative of the first times the second plus the first times the derivative of the second. That is enough work for me. If you require more work, then show more work. If you require less work, then that's okay too. I'm just giving you some advice to don't do it all at once in your head. Are you following what I'm talking about? And there's one more thing. We're going to have an I at the very end of this. Don't distribute that I. Don't do that. Just do the whole thing I. That's what that should be. One component in parentheses with the I at the very end. I don't know if you're okay with that one. We also do a lot of other stuff. You know this from your days in dealing with Calc 2. Anytime you deal with exponentials, you're going to have some stuff to factor if you have a product rule. So we get that a lot. Feel free to factor that. So if I'm factoring out that e to the negative t, I'm going to have positive, and I'm going to switch it around too. I'm going to put this in a nice order for me to look at. I'm going to have cosine t. I'm going to have minus sine t. And then I. Listen, I know it's just algebra, but the just algebra is what kicks your rear in calculus. It's the just algebra part that will get you. It's just trigonometry. That's the hard part here. So I want to make sure that I'm explaining well enough. Are you guys getting at least the derivative of the first part? You see the product rule, you see the chain rule at work, you see factoring. That's what I want. Show of hands feel okay with what I want. Tell you what, I'd like you on your own to try the next, at least this one, okay? Try that one. You'll notice something about how I teach. I teach and I review at the same time. So as I'm teaching you derivatives, we're kind of reviewing product rule and chain rule and some trigonometry and some inverses, which we're going to use later on when we deal with integrals. So I'm trying to review and teach you at the same time. Go for it. So derivative of the first times the second, that's that negative e to the negative t cosine t, that's the derivative of the first times the second, plus the first times the derivative of the second. Okay, so plus the first times the derivative. What's the derivative of cosine t dx? What's the integral of cosine t?
Sine.
Good. That's very confusing for a lot of people. Getting those confused is very easy to do. Watch your signs. No pun intended. Watch your cosines too, all right? But watch your positives and negatives. It's a big deal. So we got that derivative of the first times the second, that's here, plus the first times the derivative of the second, that's here. Here was our f prime. Here's our g prime of t. And then if we factor some stuff out, by the way, the reason why I leave it like this, I'm not worried too much about moving signs around, is when we start doing that, we start writing signs twice. We start writing negative, negative, and all of a sudden, oh, that's a positive, and we start making those little errors. Does that make sense? The more sign math that we do in our head, the more chance we get to get this wrong. I don't want that to happen. I don't want to have to give you zeros on your test because you understand everything about derivatives. You just can't get your freaking signs right. Does that make sense? I don't want to do that. So be careful with this. When we factor, we can factor that. Yeah, you can do that. You can factor negative e to the negative t out. They both have negatives. Just be careful with your signs. If you factor negative e and negative e, do we have a plus or a minus for sign?
Plus.
Good. I know for some of you, you might be wondering, why are you going so slow with signs and all this stuff? Well, because that is where you're going to make mistakes. You're not going to make a mistake on the derivative of sine being cosine. That's not going to happen. You're going to make a mistake on the derivative of cosine being negative sine, and then factoring incorrectly with that thing. I see a couple looks out there like, I'm sorry, what? Is there any questions on this so far? So far. Are we done?
No.
Pretty close though. Let's talk about h prime of t. Do you remember how to do derivatives of inverse
Yes.
functions? I hope that you do. If you were in my class for Calc 2, I hammered it in your head so much you'll never ever forget it. You're going to be like 68. You're like, dang, I remember this. Because we did a whole bunch of trig subs. And every time we got a trig sub of 1 over t squared plus 1, you went, oh yeah, tan inverse. Forget the trig sub. Done. And so you go, hey, the derivative of tan inverse has to therefore be 1 over t squared plus 1. Well, at least I hope so. Okay. If you're in my class, you have this tattooed on the front of your skull. It's like there. Tan inverse and this go hand in hand. Integral of this is tan inverse. Use that all the time. Never, ever, ever, ever do a trig sub on an integral of this thing. Because it's on the table, it's in the back of your head, it's tan inverse. Likewise, the derivative of tan inverse is always this piece. I don't know if you're okay with that one. Now, because we did each individual piece differently, that's cool, but we have I, J, K that creates a vector for us. What type of vector, I scared you, good. What type of vector does it create? Tangent vector, which the tangent vector to this curve at what point? Any point, any time, any t. It'll give us the direction of the tangent line to that curve at any time. It's pretty awesome. Let's just write it out. So the derivative is, well, all this stuff put together. Be smart about your signs. I know that when I'm doing this, I actually take these signs with me down here. I think about them. That way I can just put my pieces right down the row and not have to worry about sign changes. Does that make sense? So I'm going to take these signs with me when I'm doing my derivatives. Here, since I took the positive with me, I know I'm going to have minus. And since I took that plus with me, I know I have plus. Check my signs one more time. It looks good to me. I can't see any mistakes that I've made. Can you see any mistakes that we've made? Have you double checked your signs? Then we're good. That's it. This is going to give us the direction of the tangent vector, so the direction vector for tangent line at any point along that curve. That's a pretty cool deal. So fancy if you understand the basic concept of it. Now, let's put this stuff together. So it's always really, oh, by the way, if I ask you for a second derivative, which I'm not, could you do it? Yeah. I'd probably just start from here and just go second derivative, boom, second derivative, boom, second derivative, boom. But that's going to require a pretty hefty product rule. Not a quotient rule. You would not do that here. You would do a chain rule. You'd have t squared plus 1 to the negative 1 and use chain rule with that. Don't do quotient rules unless you have functions of t over functions of t. That's a waste of time. With me? So I'm not going to ask you that here, but you still could do it. Now let's focus on what it means. We just said they're tangent vectors, but I'm going to do an example for you here, with you here, that's going to show you how they relate to the pictures of the curves that we're graphing. Now, I gotta be honest with you. I can't draw some three-dimensional vectors real well, the three-dimensional curves, and it's pretty tasksome to do. It's not easy. So what we're going to do is we're going to focus on a 2D vector function. That way I can literally show you what the tangent vector does, how it relates to that function. Do you understand the concept here? Yes. Oh my gosh, you're looking at me blankly like I'm talking to zombies. Are you zombies? You're not zombies, are you? No. That's creepy. Okay. Welcome, zombies, to calculus. Here's the three things I want to do right now. I want to sketch a vector function. I want to identify a point of tangency. And I want to put up a tangent vector at the point of tangency. I'm going to pause right now. Is that a vector function?
Yes.
Is that a vector function that should be graphed in 2D or 3D?
2D.
Why? 2 components, 2D. 3 components, 3D. Would you know how to identify X, Y, and the X, Y, and Z components right now?
Yes.
Good. Is there going to be a Z component?
No.
That's why it's in 2D. Would you know how to sketch it?
Yes.
Perfect. If the answer is no to any one of those questions, you need to rewatch 12.1. Because we talked about all that stuff in 12.1. Okay, that's got to be there. So vector functions, I have to know that you know how to graph vector functions. You got to be able to graph these things. So that's not going to be a problem. After that, once we sketch that function, I want to find something called the point of tangency at a certain value of t. We abbreviate this with a Oregon, Washington type of abbreviation. Colorado too, no. That was a joke. No, whatever. I want to find the point of tangency at. Now listen, I can't give you a point x, y, z because all of these vector functions are based on what independent variable, what parameter? They're based on t. So I have to have it at a time rather than at a point. The time is what gives us the point of tangency. So I want this at. By the way, when you get confused about the a, it's irrelevant. It just means plug in pi over 3. So find it at a time of pi over 3. You could easily use a, this book does. You could use t, which I think is much more relevant. Find it at the time of pi over 3. So if you ever get that, at what's the a, it's just telling you to plug in that value. Does that make sense to you? They're trying to make it a little bit more muddy, but it should be just the value at which of the parameter for which your vector function is defined. And then I want to do the last thing. I want to find the tangent vector at the point of tangency. That sounds all very mathy. I promise none of it's really hard. You just got to know what to do. Okay, hey, first thing, we're going to draw some pictures here. The first thing I want to know is if you know how to sketch that. So let's go ahead and do that. And you're going to do most of the work right now, okay? So right now, if you're here listening, I want you to write down the x and the y components since there's only two. You know we're sketching on a plane. It's going to be the xy plane because there's only two components here. Write down the x and the y components, and I want you to try to translate that into something you can graph. Go for it. Some of y'all are just not even doing it. Either you're done already or you're just waiting for me. Don't wait for me. Try to do this stuff. You have to try. You have to at least try to internalize it. It's really horrible just to be passively watching the screen as I am right now for you, just a person doing math. Unless you're stopping and actually doing this, it's not going to sink in as well as it could. Right-siders, I think I did last time. Right-siders, what's the x component? And the y component? And the z component? Which is why we're graphing on a plane and not in 3D. So this is going to be a vector function for sure, but it's going to be on a plane. Now, I gave you a piece of advice. I said use one or two components to sketch these things. If you only have two, you're probably going to have to use two to make some sort of a curve that you understand. Essentially, you need to get rid of t. Do you see anything, middle people, that's going to allow you to get rid of the t? I also gave you advice on that one. What would you do when you get this on a test? That's right. Pythagorean identity is a really good idea when you have sine and cosine raised to the first power. So we'd solve for cosine t and sine t. And I know this works all the time. Cosine squared and sine squared when you have the same variable equals 1. Which means if I have that substitution, I can do cosine squared plus sine squared equals 1. Now, I don't know, to me that looks a whole lot more understandable than that because we're very used to rectangular coordinate systems and not really parametric systems. Do you know what that looks like? Perfect. On what plane? So only two variables. Is it a cylinder going through 3D? No, because there's no third component. This is flat on a plane. Or if you want to be really fancy dancy, there is a third component, and it's 0. Oh, flat on the plane. Hello. It's the same thing. That's why it's on the XY plane. Does that make sense? That's kind of cool, right? You didn't even know. What? Maybe you probably did know, but still kind of neat. Let's go ahead and sketch that. So everybody right now, go ahead and sketch that. Make it a nice big sketch, okay? We're going to do some stuff with it. Yeah. I started off pretty good. Didn't end that well. Not even try. No matter what I try to do, they always end up looking like Stewie heads. You know what I mean? Every single time. I can't do it. Can't do it well. Fortunately, we're going to focus on this area, but I can't leave it like that, dude. It's videotaping. I got to make it better. Sorry. You ever get that way? You got OCD like me? Is that better or worse? I can't even tell. We're going to give up on that one. Okay, please listen carefully to what I'm about to tell you. This right now, we did it in 12.1, but I'm going to reiterate it. This is not your vector function. This is the curve upon which your vector function falls. There's a slight difference there. You see, your vector function has a certain domain to it. Your vector function starts somewhere and it ends somewhere if you have a defined domain for that. If you don't, it just keeps on going forever along the same route. Does that make sense? But no matter what, it certainly has an orientation. So this vector function, what it does, it starts at t equals 0, which if you plug that in, you know this from when we did vector functions. You plug in 0, you're going to get 4, 0. 4, 0 is there. Your vector function starts there. Does that make sense? The next value you plug in, probably something like, I don't know, pi over 2, you're going to get 0, 2. Oh, yeah, okay, it hits here next, which means your vector function progresses from here. It goes along your curve. It can't go anywhere else. It hits this spot, which means it's going in that direction. Does that make sense to you? It's going to keep on going to hit pi. It's going to hit 3 pi over 2. It's going to hit 2 pi, and it's going to stop right there. It terminates there. So it does one lap around this track. There's one lap in this direction. Same way you'd run a track in track. Show of hands feel okay with that one. Did you guys get the nuance of that? How the curve you draw is not necessarily your vector function. It's just the curve that you're laying your vector function on top of. It's not discussed very often, but it needs to be. That's what's going on here. So we go one lap, that direction, that orientation. For sure, you okay with it? Now the point of tangency. This does not have to be hard. What up here gives you points? Sort of the vector function. The vector function gives you vectors. But at the end of that, the terminal point of that vector is your point. So if I want to find the point of tangency, I want to find the vector that points to that point of tangency. How you do it? Man, plug it in. All you do is plug it in. So in order to find the point of tangency, man, just plug in that value of t. Just plug in t equals pi over 3 into that vector function. So I want to figure out essentially that. That's what I want to know. Can y'all do that for me, please, real quick? Would you do that? What happens when you plug in pi over 3 into your vector function? What's cosine of pi over 3? Do you know? 1/2. 1/2. Very good. So we have 4 times 1/2, and we have what? 2 times root 3 over 2 because sine of pi over 3 is root 3 over 2. Show of hands, feel okay with that one so far. Unit circle, man. Have it down. Question. It's a slight thing, but question. Point or vector?
Point of it. Yeah.
Both.
Okay.
Both. It is a vector, and you're going to simplify, of course. You're going to tell me that the vector is 2 comma root 3. That's the vector. Are you listening to what I'm talking about? So there's a slight little change here. What this is the vector that points to the point of tangency. The terminal point here, that is what is the point of tangency. So this vector is given, it's right there, I mean, it's given it to you. But the point of tangency is now 2 root 3. Here's how that looks. Here's how it looks. Here's 2. Go right up there. Use purple here. Here's 2. Here's 2 comma root 3. 2 comma root 3. It has to be on that vector function. That's how we even found it. Okay. This right here is the point of tangency. Here's how the interplay works. Please notice. Please notice. Look. This vector, that is a position vector. That position vector from the origin points to x component of 2, y component of root 3, it points right there. That's what the vector does. This is the vector with a value of pi over 3. It points to its terminal point, the point of tangency, which is the point 2 root 3. I know it's very, very similar, but there is a slight difference there. The point of tangency is the terminal point of that vector. That's the idea. Show of hands if I explain it well enough for you guys. Now, maybe a 10-second recap before we get going. You know how to sketch vector functions, use a couple components, get a curve that's understandable to you, and overlay the vector function on the curve. That's what happens for whatever domain you have. How we find point of tangency is very easy. I have to give you a value in order for you to find a point of tangency. So you plug in that value, it gives you a vector that points whose terminal point is the point of tangency. So slight little difference, but here's the vector, terminal point is the point. That's pretty much said and done. You guys okay with that one? Now, let's use our calculus. What I know is that if I want to find a tangent vector at the point of tangency, what gives me tangent vectors? Derivatives. If you had, man, it's like being back in Calc 1, where if you don't know the answer, you say, derivative. Hey, you're right. You're a genius. That's exactly right. If you don't know the answer, it's derivative. Every time you hear the word tangent, it is probably going to do with a derivative. So let's find the derivative. Go ahead, do it now. Find me the derivative or the direction vector of the tangent to this vector function at any point. This one shouldn't be too tasking. Do you need a product rule for that?
No.
Okay. Yeah, don't waste your time. What is it going to be?
-4.
If I use vector notation, I don't need the i's. But you can put them if you want to, if you don't use the vector brackets. And then I'm going to have what?
2
Head enough, you're okay with that one so far. Now, what is it? Come on, put it together. What is this thing? What's it mean?
Direction of a tangent vector.
Good, that's a tangent vector. That's all it is. Now, I want the tangent vector to be at the point of tangency. So, what value gave me the point of tangency? Plug it into here, and you have the tangent vector at that point. That's pretty impressive, right? That's what that gives you. So, if I want to find out the tangent vector at the point of tangency, I find the tangent vector at the value that gave me my point of tangency. And that's pi over 3. Oh, I forgot my prime. Don't forget your prime. I do it all the time. You got to catch me. That rhymed. That was really awkward. Sound like Billy Madison. No, Happy Gilmore. Listen to what I say. Shoot, I did it 3 times. Focus. So if I put in pi over 3, I've got, let's see, sine of pi over 3 again. What's that one? So negative 4 times root 3 over 2 looks like negative 2 root 3. Did you guys get the negative 2 root 3? That one, I know that's, well, it's still 1/2, so this is 2 times 1/2, which is 1. I want to know if you're picking up what I'm laying out. You guys understand that? Drew?
Got it.
Got it, cool. Sketching, you know how to sketch. Point of tangent, that's a new one. That's not hard. Just plug the point in. It's like when you say, hey, find the equation of the tangent line to a curve. You actually have to plug the point in, the x value to find the point, right? This is like the x value you're plugging in to find your point. That's the point of tangency. Now, to find the tangent vector, derivatives give tangents. I don't care what class you're in, derivatives give you tangents. So we have the equation for our tangent vector. We have the actual tangent vector at that value, at that point. So we have this tangent vector now. Now here's the deal. If you know anything about tangent vectors, if vectors at all, this is a position vector, right? Position vectors normally start at the origin. This vector would be negative 2 root 3. That's over here somewhere. And then 1. It's pointing like that. That's how that tangent vector is looking. Well, we have the idea in vectors that we can move these things to put initial points at different points. If we take this and we move that initial point to the point of tangency, so put this, so its initial point is at the point of tangency, I'm going to make a little blurb about that. Put initial point at point of tangency. That right there is a tangent vector. And now I'm kind of cheating on the magnitude because I don't know how long it is, but I know that this right here, what we just found, is the direction of the tangent line to this vector function at that particular point. That's what we found. That's pretty impressive to be able to do that. And what's more impressive, we're going to be able to do this in 3D. That's not a plane, but the idea is exactly the same. Do you guys understand the idea? Sketch the vector function like you know what you're doing. Plug in the value to get the point of tangency. Find the derivative. Derivatives give us tangent vectors. Plug in the same value, and you get the tangent vector at that point. That's pretty cool. What's even cooler here, even if you just know that the vector function lies on this thing, and you don't even want to worry about orientation, here's a big one, though. It's a big no. It's pretty cool. Your tangent vector will always give you the orientation. Has to. It says, hey, what direction is that point moving? At that instant in time, you remember about tangents, they give you the instantaneous rate of change. They tell you where it's headed at a moment in time. That point is headed that way. The orientation has to be this way. Isn't that kind of cool? So we'll always give you orientation. So tangent vectors also give, write down that blurb, okay? Tangent vectors also give orientation of vector functions.
So if your tangent vector is going the opposite way, something's wrong?
You did something wrong. Yeah. If you have, oh, my orientation's this way for this segment, okay? Now, you can change with some weird functions. You change back and forth. But if you have, my orientation is going this way for this time interval, the domain of my parameter, and then you find a tangent vector is headed the opposite way for that specific time interval, you've done something wrong. Now, it's weird, you found this parametrically, weird functions oscillate back and forth. So you have to match up the domain, though. Does that make sense? You plug in some different values of t, yeah, you're going to get some different directions. It could be changing orientation. But for a given orientation, or for a given, let's say, tangent vector, it gives orientation for that specific domain. I'm going to make it much more simple. Tangent vector gives orientation. All right? Tell you what, we're going to pause right there. When we come back, I'm going to do one more example of this. Then we'll talk about these things called unit tangent vectors. I want to give this some time to sink in, about 10 minutes to sink in. When we come back, we'll do one more example. It'll be, if you give yourself some time to really let this absorb, it'll be very clear when we come back. We'll talk about unit tangent vectors, which is like, what's that mean? We'll talk about it. Then we'll talk about how to find equations for tangent lines. After that, we'll talk about some integration, and then we'll wrap it up. Okay, so like I said, one more of these examples. We're going to go pretty quick through it. I just want to make sure that you can do it. Hopefully it's sunk in a little bit more in your heads. We'll talk about what a unit tangent vector is. One quick example, probably not so quick, it's Leonard. After that, and then we'll talk about tangent lines. Tangent lines to space curve. When we get done with that, when we find the tangent lines to space curves, we'll do two examples. Then we'll talk about integrals. Integrals are not rough. They're very, very easy if you know the techniques for integration. Calc 2, if you know that, then this is very easy. The only thing, like I said, that gets a little tricky is when you have initial value problems, and that's where we're going to spend most of our practice, is just practicing this stuff and trying to crush it. Make sense? So here we go. Oh, goodness. Vector function, yes, no?
Yes.
2D, 3D?
2D.
Good. What plane? Perfect. I'm not going to sketch this right now. I don't really... Well, you know what? You want to try? We can try. Let's write down the x and the y components. Go for it. Now, the idea on sketching this, if we wanted to sketch it, which I guess we can, it's not that big of a deal, the idea is to get rid of the t. Do you see a substitution that's going to allow you to get rid of the t?
Yes.
Substitution. Not tricky stuff. Not tricky stuff. Something lets you put this here. What if I do this? What if I do that? Does that work for you?
Yeah.
Now do you see a substitution? Sometimes you have to manipulate this a little bit. If you will. Like that. Did you guys get the idea on that? Now, I didn't give you any domain for t, so you have to assume it goes from negative infinity to infinity. Do you know what that curve looks like? You should, because it's my third favorite dance move ever. 1 over x and negative. And then we got, well, absolute value. I mean, negative. That's the second best dance move ever. You do that in the club, you're like, money, buy me drinks, right? I don't know, I don't go to clubs. So, but I assume in my head, if I wasn't a math major, I would have gone and had lots of fun. But I was a math major. No fun. And then you got 1 over x squared. You get this one. And that's what this is. So this curve looks like that. That's the curve that this vector function will be traveling along. Now, how it travels? Well, you can do a couple things here. You can actually plug in some points and see where it's traveling along, or you can wait. You can figure out what the vector function is, what the tangent vector is, and you can give the orientation that way. Now, here's one thing I do know, okay? Because I'm not giving a domain, you assume that that domain is a natural domain, which goes from negative infinity to infinity unless we have some restrictions, which we don't. Here, you can plug in anything to exponentials. Do you follow what I'm talking about? So I know that the vector function is going to complete this whole graph. The only thing that I'm confused on right now is what directions it's headed. I don't know where it's actually headed. Does that make sense? Again, you can plug in values to figure orientation, or you can wait, get a tangent vector, and see where that shows for you. Head nod if you're okay with that one. So this was a little above and beyond. We actually sketched it, but it's not a huge deal. What's the next thing that you would do here? If I wanted to figure out the tangent vector at t equals 0, what would you do? In order to figure out a tangent vector, and actually graph it, I need a point where that tangent vector is going to start from. What's the word for that? What's the phrasing? I want the point of tangency. Can y'all right now find the point of tangency for me? Everybody, real quick, how do you find the point of tangency? What do you do?
Plug in 0.
Plug it into where? The vector function is going to give you a vector that gives you terminal points which are on the graph. If it's giving you terminal points on the graph, and I want the tangent vector at that point, that's called the point of tangency. So plug in the value of t to your vector function. Hopefully I did it right. Did you get 1, 1 also? Plug in this number here. It gives you a vector that's pointing to a spot on the graph where you are going to create a tangent vector. Does that make sense to you? That doesn't make sense because I can tell in your face you're like, what? I'm sorry. Let me rephrase that so you guys, I want you to listen though this time. What this does, it creates a vector that's pointing to the spot on your graph where I want the tangent vector. That's called the point of tangency. So the terminal point of that vector is the pot. Does that make sense to you? Do you guys get that idea? Show of hands if you do. You understand that idea? Good. All right. Fantastic. So I know that whatever I do next, if I find the what's going to give me tangent vectors? Come on. What's going to give Jimmy? If I find the derivative of that vector function, it'll be a tangent vector at any point. And if I plug in 0, it's going to give me the tangent vector at that point. That's what's going to happen. Do it. I love exponentials. Don't you just love exponentials? Just don't forget the chain rule, please. I'm begging you. I'm begging you. Please don't forget the chain rule. We can't avoid getting that -2 by the chain rule. Hey, now if you're okay with that one. What is it? Don't just do math blindly, man, because when you get to the test, you're going to forget it. And then you go, I don't remember what this is. What was all this used for? The sketch. What's plugging in a number? What's plugging in the number for this tangent vector at a point? What's plugging it in there giving me? What's that?
Point of tangency.
It's giving me the vector that points to the point of tangency. The terminal point is the point of tangency. What's a derivative of a vector function giving you?
The direction. The tangent vector.
The direction of the tangent. It's giving the tangent vector. The direction of the tangent vector, or the direction of the tangent line to that curve. We're going to use that in just a minute. At what point?
0.
You know, it seems pretty silly to find a point of tangency and then use a different value here, right? Because if I want a tangent vector at that point, I'm going to use the same value. So the tangent vector at 0 gives me that vector. Please don't change that to a point. Don't change it. It's not going to be on your graph. Okay, it's not going to be there. What it's telling you right now is that 1, -2, that's the direction of the tangent vector. That's where it is. Where we locate that tangent vector is from the point of tangency. So from that point, check this out. Watch carefully though. It's easy to do here. From this point, the tangent vector, initial point's here, at the point of tangency. This has an x component of 1, and a y component of -2. Do you guys get the same vector that I got? So from here, it'd be x component 1, y component -2. It's going to look like that. That's what that tangent vector looks like. If you put the this initial point at the point of tangency, now my graph is not exactly right because I just sketched it. But that's generally the direction of that tangent vector from that point. Head nod if you're okay with that one. What orientation is it going?
No.
This way?
No.
This way.
Yes.
Now you can find, at least for this part of the graph, you can find the orientation now. To find the orientation here, you'd have to do another tangent vector at a certain point over there or plug in some values. Because I don't, it's probably going this way, but it doesn't have to be going that way. Does that make sense? So this I know looks like that. And for the money, if you were actually doing this, it's pretty quick. It's a pretty quick way to sketch a tangent and to get orientation of a curve. Am I making sense? Now, we have done a lot of work with tangent vectors right now, and we've also done a lot of work with unit vectors. Remember what unit vectors do? Unit vectors.
Point.
Direction. Have a length of.
One.
So a unit tangent is a direction of a tangent that has a length of 1. So we're going to do the same exact thing. We're going to find tangent vectors, but we're going to divide by the magnitude to make sure that we have a unit tangent vector. There's a special name for that. There's a special notation because it happens so much. We're going to get the first part of this trifecta of pretty cool things called the TNB frames. Frenet-Serre, I think I pronounced that wrong, but Frenet-Serre, I'm not good at that. Frames, TNB frames. It's a movable frame that can travel with a particle. And we're going to do the first little part. It's called the unit tangent. So a unit tangent vector, it's not fancy, okay? It's not. All it is a tangent vector that has a magnitude of 1. You know that. You know unit means 1. You know tangent means, well, a derivative, and unit tangent would be a derivative where we divide by the magnitude. So when we have this tangent vector that has a magnitude of 1, we have this notation. This right here is the unit tangent vector. We call it capital T. We put a little vector above it because it is a unit tangent. The only difference is we don't have a hat. That capital T stands for the unit tangent. Head nod if you're okay with that one. How are we going to do it? Well, you probably already know. How do we find a tangent vector? Right now, how do you find a tangent vector? What gives it to you? A derivative of a vector function gives you a tangent vector. With me? How do we make something be a unit vector? How do we make a unit vector? So if we have a tangent vector and we divide by the magnitude of said tangent vector, we get a unit tangent vector. Oh, yes, sir. Going old notation on you guys, my bad. Tangent vector? Yep. Magnitude of tangent vector? Yep. Unit tangent vector. That's what we're talking about. You with me? You want to try it? You'll try it right. I bet you can do it right now. Here's what I want to do. I want to find the, what's it stand for?
Unit tangent vector.
And the point of tangency at t equals, oh, what I have down? Pi over 6. What can you find right now with doing very little work? What can you do?
Point of tangency.
You can find the point of tangency really easy. How do you find the point of tangency right now, everybody? What do you do? Can you do that? Let's find the point of tangency. Plug in pi over 6. 2 times pi over 6 is pi over 3. Sine of pi over 3 is what now? Tiers of sets.
Sine of pi over 3 is
root 3 over 2. So when I plug in pi over 6 here, I get pi over 3. Sine of pi over 3 is root 3 over 2 times 2 is square root of 3. Did you get square root of 3? Now we have IJK notation. You can switch it. I don't care. I don't care. All I care about is that you find the point of tangency. Listen, folks, the point is not a vector. The vector gives you the point, but the point is not a vector. The vector points to the terminal point of that vector is a point of tangency. So IJK, whatever, it doesn't matter. Plus pi over 6, so 2 times pi over 6 is pi over 3. Cosine pi over 3, that's the 1/2. 3 times 1/2 is 3/2. Hey, let's plug in pi over 6 there. What do you get?
Number 3.
3. from here, can you give me the point of tangency? Keep in mind what we're doing. What we just found is practically this vector that points to that one point where I'm going to put the tangent vector. So our point of tangency is square root of 3, 3/2, 3. Now we're not going to graph this thing. I don't want to spend the time to do that. We're not going to graph this thing, but we're going to go through all the motions of find a point of tangency and then the unit tangent vector. Y'all still with me? What's your next? So we have point of tangency. That's fantastic. What's the next part if I want to find the unit tangent vector? What would you do? Do you understand why you're doing that? If tangent vectors are given by derivatives, the unit tangent vector is given by derivatives, but just a little more, divided by the magnitude of that derivative. So right now, in order to find the unit tangent, the first part of it is finding just the regular tangent. Go ahead and do that now for me, please. Let's make it pretty efficient if we can. Go quickly, don't make mistakes, but go quickly through it. I'm going to give you about 30 seconds to give me the tangent vector. Always forget it. Hey, what's probably the main rule you don't want to forget here? What's my first coefficient if you know how to use the chain rule properly? Perfect. 4 cosine of what?
2t.
Beautiful. Love it. Plus or minus?
Minus.
Great. Plus or minus what?
6.
Love it. You guys are awesome. And then? Plus 0. Nothing. Awk. Don't write awk. You don't need it. Okay? Just end with the J. You're fine. So this, what is it? What is it? Did you catch that joke? It's funny. It's best it gets. What is that thing?
Tangent vector.
That is the tangent vector. Is it the unit tangent vector?
No.
How do you find the unit tangent vector?
Plug in the
Oh my gosh.
pi.
Can you find the magnitude of that? That's what I'm asking you for. And we haven't done it very often where we've actually had variables in there. Can you do it? Can you find the magnitude of that? It's done the same way. Remember how to find magnitude of vectors? Square them, add them, square root them. Square them. Add them. Square root. Okay, here's the deal. Please listen here. If you have to give me the formula for the unit tangent vector, it's right here. You just divide them. Here's the tangent vector divided by the magnitude. That's the formula. Do you guys get what I'm talking about? If I have a specific value, then if I want to find the unit tangent at a point, so at pi over 6, you can do it a couple ways. Honestly, I hope that you're seeing that this little difference here. I did this way because we have to do it later. We have to find the formula for the unit tangent. It's part of what we do in this class for TMB frames and curvature and torsion and osculating plane. We're going to do all the stuff that's going to make sense in 2 sections, okay? You know, oh yeah, it makes sense. We have to get these formulas for that. But if I were doing this like just this, and I wanted just the unit tangent at pi over 6, you know what I would do? Did this make sense to you? That you can do this? Okay, so this right here, that fraction is the formula for the unit tangent. Right now, if you want to plug in pi over 6 to all of this junk and work it out, you're going to get the same exact thing, and I'm going to give it to you a slightly easier way. But I wanted to show it to you now because we're going to have to do it eventually. Does that make sense? If you know that you're finding the unit tangent vector at a certain value, you can do this. plug in pi over 6 here and find the magnitude of just that vector. Does that make sense to you? And then that saves you the work of having the nastiness. If you don't have a specific value of t, then you have to have the nastiness. If you have that specific value, then you go, okay, well, hey, what's that? What's the specific tangent vector? So I know my point of tangency. The specific tangent vector would be, well, find the tangent vector at that value. Plug in pi over 6. Well, we go, okay, pi over 6, pi over 3, cosine pi over 3 is 1/2, so this would be 2i. That's pi over 3, sine pi over 2 is root 2, so minus 3 root 3j. If I've done my math right, but I need to double check. I make mistakes sometimes. Did you get the same thing I got?
Yeah.
Tell me something. What's easier to find the magnitude of? This guy or this guy? This guy. So if you don't have specific t, yes, you need to find the magnitude of this like I showed you first. That would be how you find the unit tangent. If I say, hey, just find the unit tangent at a specific value, plug it in first, and then when you find the magnitude, I gotta drop that down a little bit. Then when you find the magnitude, you're dealing with actual numbers, real numbers, and it's easier. Magnitude works the same way though. Square them, add them, square root them. So when we square this, we get 4. When we square this, we get 27. 2 squared is 4, 3 squared is 9, square root of 3 squared is 3, 3 times 9 is 27. If I add those together, we get the square root of 31. Are you guys okay on the square root of 31? Listen, if you're watching the video, or if you want to go back and check this out, take that nasty expression that we had right here and plug in pi over 6. I guarantee you're going to get this over the square root of 31. That's exactly what you're going to get because it's exactly the same. We just save ourselves some trouble when we find the magnitude of a specific vector, if you need to do that. Show of hands, you understand the difference in those two things. Now, how do we write the unit tangent? Man, be smart about it. We know that the unit tangent is going to be the tangent vector divided by the magnitude of that tangent vector. It's going to be 2i minus 3 root 3j divided by the square root of 31. That's literally it. But it's hardly ever how we see, it's never how we see an actual unit vector. What do we do with the square root of 31? What do we do with it?
Rationalize.
We rationalize it and we...
Pull it out.
Please. I know some books do this. Don't distribute it. It's freaking crazy, okay? Here's why it's crazy. Because, listen. If you distribute that square root of 31 over 31, you're getting some pretty nasty stuff, right? Really nasty stuff. The problem is, when we do this thing called the TNB frame, when you get the normal and the binormal vector for the osculating plane, for all the stuff that we're doing, if you have that distributed, your work gets a million times harder. If you have it out in front, are you listening? You can find the magnitude of your vector and just put that back, and you have the tangent normal and the binormal. It's way easier. So when you're dealing with unit tangents, especially, rationalize it. All right, you can do that. You don't have to do it. I don't really care. You can leave it 1 over the square root of 31. I don't really care. Some books really care, but in my opinion. Which, I mean, is really what matters, right? I mean, come on. In my opinion, don't ever distribute that unless you absolutely have to. Sometimes you have to, but don't do it unless you have to. Show of hands, feel okay with that? Now, what's it mean? We've just trudged through a lot of math pretty quickly, not too bad, but don't get lost on what we're actually doing. What are we doing? What is this piece of junk that we've... What's this thing?
Tangent vector.
No, this. What's this?
Oh,
vector.
It's a curve. It's a vector function. It's a curve. Get it? What is this?
tangent vector to a point on the curve.
This gives me the tangent vector at any point along that curve. What is this? Okay, let's go through here. What is this? Curve. Tangent, a vector function is a curve. What is this?
Tangent
Formula for the tangent vector at any point. What is this? The actual tangent vector at that time point. At that point. At this point. At this point. Because that is the point at that time. Does that make sense? Curve, equation for tangent, vector, direction. Actual tangent vector at that point. This. This vector shrunken down so that it has a length of 1. The unit tangent. That's exactly what we're finding. In other words, the direction of the tangent line. If this is a curve and that's the tangent vector, this is giving you the direction of the tangent line. This is literally giving you the direction itself. No length, the direction of the tangent line. Question. What two things do you need to make a line in 3D? A point and someone else.
Vector.
A vector. A direction vector. So, what two things do you need to make the equation of a tangent line? I hope you listen. This should be exciting. We're almost to just the point of why we did all this junk, okay? What do you need to make the equation of a line? Point vector. Point and direction vector. What do you need to make the equation of a tangent line? A point of tangency and a tangent vector. You need one of these two things. If you need a unit, which you rarely do for tangent lines, we use this for later. Okay, this is for later. But we need at least a tangent vector and a tangent point. That's what we need. And that's what we're going to use in the next little blurb that we're going to talk about. So what we found is essentially a vector. I hope you're catching it. We found a vector that's parallel to a tangent line. It's a position vector, right? So we can move that through a certain point. We go, hey, here's my point. Oh, that point. Move this vector through that point, aka the equation of a parametric line, which we did in 11.5. If I move this vector through that point, I have a point, I've got a tangent vector, I have a tangent line. That's the point. That's pretty cool. Can you use the unit tangent? You can, but it's a lot messier. Remember with vectors, every vector that's a scalar multiple is parallel, correct? So when I'm talking about lines, pick the easiest one. We're going to use this for later for moving frames, TNB frames. We do use it for curvature and things like that. We're going to have to do this. But as far as tangent lines are concerned, you need a point and direction vector. Here's the point. Here's the vector. We can now make tangent lines in 3D. That's the point of this section of our class. Let's do that a couple times, and then we'll continue on to integrals. Listen, at this point, I've talked a lot. My voice is tired. I'm not going to stop, though. I'm here for you guys. So, and I get paid to do this. It's awesome, right? I get to hear my own voice and teach math. And you guys have to sit here and listen to every word I say. I love this job. And I get paid for it. Woo! Not a lot, but I mean, it's something. So, better to sit than nothing. Do you guys get the idea? Do you understand the idea that this is a freaking curve through space, and that vector gives me the direction of the instantaneous direction of that particle as it moves along the curve? And if I have a point, that's the point where that's taking place, the actual vector, and if I divide by magnitude, I get the unit tangent, the literal direction that that particle is headed. That's what I'm talking about here. Do you understand the concept? Show of hands if you do. Okay. Let's talk about lines and math. So since I already talked about it, it should be pretty straightforward. I'm just going to write down a couple blurbs note-wise for you to take. So for tangent lines, literally one more step. That's all there is to it. So for tangent lines, any line through space, any line, tangent line or otherwise, needs two things: a point and a direction vector. Well, if you make it more specific, tangent lines need a point of tangency and that looks pretty funny. No one needs it, I get. Well, medicinal? I don't know. I'm not going to change it. I don't care. Whatever. California's going to have it soon, I bet. Almost guaranteed it. Probably. So, tangent lines need two things. Any line needs two things, a point and a direction vector. Therefore, tangent lines are very specific. They need a point of tangency and a tangent vector. At the point of tangency, the tangent vector is the vector that gives the direction of the tangent line. If you put it on or through the point of tangency, you literally have the tangent line. Point, vector, line. That's what we're about to do right now. So for the point, use point of tangency. For the direction vector, how do you find a tangent? Everyone in class right now, how do you find a tangent vector? What gives it to you? Oh, that was average, like 2 people. In this class, what gives you a tangent vector based on a vector function? Derivative. For the tangent vector, use the derivative at, the same value of t that gives you the point of tangency. At t that gives you the point. That's the best I can do, so notation-wise. Listen, it's really similar to Calc 1. If you want to find the equation for tangent line, you need slope, you need point, right? You take a derivative, it gives you slope. You got a point, hey, point slope. Here it's the same thing. You need a point, you need a slope, but our slope is no longer a slope. It's just called a tangent vector because lines in 3D are parametric and they're given by a direction vector. That's what we're doing. So we're just going to do like 2 examples here. We'll talk about some rules for differentiation, and then we'll start our integrals, and we should be all kind of happy about that. Is this understandable for you? Yeah. Easy, medium, hard? Usually after chapter 11, people are like, thank you, it's calculus, because I understand what derivatives are. It's the same idea. Derivative means tangent or slope, direction of the tangent line to a curve at a point. It's the same thing. What point? Point to tangency. What direction? The tangent vector. That's the idea. Let's go. So exciting. Told you it was going to be riveting. Are you riveted? Have you ever seen a rivet gun work before? You don't want to be riveted. It hurts. Yeah, pop rivets and skin, they don't mix. Did I ever tell you my skill saw story? Back when I used to work construction? Did I tell you that story?
No.
I'll tell it to you someday. Not today. Maybe I'll just have videos of just stories. Story time. No one would watch it. Ever. My stories suck, you know that. So anyway.
Have the most views.
If those get the most, I'll be so sad. Do you know how hard I work to make these stupid videos? If I get views on stupid stories about skill saws more than this, the cats playing with yarn get more views than Calculus freaking 3 doing tangent lines in 3 dimensions like our world exists. And the kitties are funny though. Charlie bit my finger. I don't even know what that means. I refuse. I refuse to look it up. But it's got like 1 billion views, apparently. Don't look it up. Don't waste people's time with that nonsense, all right? They went on like Oprah or something because of that. Here this is Calculus 3 doing freaking awesome math that no one else does, and Charlie bit my finger. That's better somehow. That's my rant for the evening. Enjoy that. Listen, I want to find test question on anybody's test ever is this question. Find the equation of the tangent line at a certain time. Listen, if you want to find the equation of a tangent line, you have to be given a point or a way to find it. So I cannot tell you, find the equation of the tangent line, go. That's impossible. I have to tell you, find the equation of the tangent line at least a value of t. Does that make sense to you? So find the equation of the tangent line. Probably 2. Let's pick 2. I think I probably would have picked a good one. Yeah. Find the equation of the tangent line at t equals 2. Okay, everyone in class right now, what 2 things you need to make the equation of line in 3D? What 2 things you need to make the equation of line in 3D? Point and direction vector. Those are 2 things you need. The equation of a tangent line means a point of tangency and a tangent vector. Find the point of tangency right now. Go. Man, this stuff is good, right? Can't sleep through this. Eye roll, as some of you are sleeping. How do you find the point of tangency? You find any point by using a function and plugging a number in. So same thing here, you guys were right. Please don't let the fractions bother you. You don't do a whole lot of work with them. They're just going to be there, okay? So don't let it concern you. You got a fraction button on your calculator, which is what I want for you. You got fractions handled, okay? So don't worry about them too much. Don't let them intimidate you. Did you all find this? At least this. True or false? This is the point of tangency. True or false? This is the vector that points to the point of tangency. There's a slight difference there, but know the difference. So the point of tangency is this point. Two, 1/3, 1/4. That's pretty. This is what's going to happen. And this is pretty amazing. The next vector we find is going to be the vector that has the same direction of the line that hits this point and is also tangent to this curve. This is the whole idea here. You need a point and a vector, right? We have now a point of tangency. We now want a tangent vector. Everyone in class, what gives you a tangent vector to a vector function? What gets it? Let's find the derivative. Go for it. You know, do whatever it takes to make it so that you can do those derivatives appropriately. I don't care how fast or slow you go in this class. In Calc 1, I'd make you show every work, but this ain't Calc 1. It's not Calc 2. If you have a calculator that does derivatives for you, I don't even care. That's not the point anymore. We're not in the business of just hammering derivatives over and over because we're way past that. The idea in Calc 3 is pretty awesome because you're hopefully understanding what the derivatives are doing for you. We're finding tangent lines to curves through space. That's pretty cool. Instantaneous rates of change of particles, how fast they're moving, what direction they're headed in if they're traveling along this particular curve. That's what we're doing. I'm not concerned about how many steps it takes you to go from here to here. If you know the 1/2, a chain rule, good, it gives you 1, subtract 1, move it down to the bottom, that's fine. If you know that you don't need a quotient rule here, you just have -1, chain rule, okay, it's cool, -2. If you know that you do need a chain rule here, 2t times 2, that's 4t, but we have the negative, move it down, you get a square. Double check me, but I'm fairly certain that that's correct. Did you guys get the same thing I got?
Yeah.
At least a triple check. You guys over here? Perfect. What is it though? We spent a lot of time doing this derivative. What is this thing?
Tangent line.
Tangent
Vectors.
tangent vector. Can I find the specific tangent vector at the point of tangency?
Yes.
What number would I plug in right now?
Sure.
Can you do that for me? Whether you got this that fast or not, that's okay. Write it down, plug in 2. I know you can do derivatives. think. No, that's
Should be
wrong.
1/8,
Yeah,
right?
1.
Because that's, yeah, 8 squared, 64.
Yeah.
My bad. It's 16 in my head somehow. I think I multiplied by 2 instead of squared. I have it right here. I can just look at it. That's pretty smart. Point, yeah, looks good. Cool. Did you get the same thing I got?
Yeah.
Let's think about what we just did. What two things? I know I'm being redundant. I don't care. I want it to sink in your head. I want to brainwash you right now. I want to make sure it sticks. What two things you need to make the equation of line? Point and direction vector. For a tangent line, you need a point of tangency and a tangent vector at a specific point. Do we have a point of tangency?
Yes.
Do we have a tangent vector?
Yes.
Point of tangency, done. Tangent vector, done. We can write the equation of a line. If you remember what the equation of a line is. Do you remember all of 11.5? It wasn't irrelevant. It comes back. All of chapter 11 is used in this entire course. It's why we covered it. If I could have just skipped to chapter 12, freaking would have, okay? But we can't, because you have to know how to write equations of lines and planes and things like that. We're talking about lines, and the way lines worked was that. Do you remember that? It was parametric. And y was likewise, z was likewise. It was, oh goodness, what are these three things? Come on, fill this
Time
out.
variable.
These are
Points.
the coordinates of the point. What's A, B, and C?
The vector.
That's the direction numbers of our direction vector. This is your point of tangency. This is your direction vector. I'm using the A here to signify that we've actually plugged a number in. Okay, you don't use T because that T is right there. Okay, you don't want to get that confused. The A stands for the actual value of that T, the actual tangent vector. Does that make sense? So when we do our lines, we go, hey, what's the line? You do it for me. Here, right side. Give me the X, please. Oh goodness. Okay, left side. You get your chance then. Fine, whatever. You don't play along. Forget you guys. Left side. You give me the X portion, the X coordinate of our line. What is it? 1/4. It should be 2 first. It should not be 1/4 because the way that lines work, you give point, then the vector component. So it starts with a 2. Now you wrap it up. What's the next part? Yeah, plus 1/4 T. You guys okay? Middle people, you get the next one. Give me the y coordinate of our line. What's it start with?
1/3.
Beautiful. Plus or minus?
Minus.
Love it.
190.
I'm running out of space, but we'll do z. Ugly. Ugly. Right side, you get your last chance here. What's the... then you're fired, like Trump. What's the z?
God.
1/4.
And then?
Plus.
No.
Minus.
Minus.
You're paying.
Oh, I'm paying attention. Can't help it. Did you remember lines?
Yes.
Do you remember how to do lines? Lines are, you take your point, x, y, z, you take your direction vector, x, y, z components, and you put them there. This is the parametric equation for a line. Could I ask you, oh man, digging back, could I ask you for the symmetric equation for the line?
Yeah.
Would you know how to do it?
Yes.
Solve for t, you'd have like x minus 2 over 1/4. You leave it as the fraction. It's nasty, but you leave it as a fraction. You'd have y minus 1/3 over negative 1/9. You leave it as a fraction and the negative. You'd have z minus 1/4 over negative 1/8. That would be the symmetric version of that. Listen, you need to know this for your test that's coming up. You got to be able to find equation of lines. Okay, there's no joking about it. You have to be able to do that. It's not hard. None of this is hard, but it's so much to remember. That's what makes it hard. You got to know what to do with your point and with your line. So here's your 10-second recap for this. Anytime you want a tangent line, you got to have a point and a direction vector for any line. You need a point of tangency, very easy. Plug in the value, done. End of that vector is the point. Tangent vectors are always derivatives at the same value of t. So find the derivative, plug in the value of t. When we want the line, we have point combined with direction vector, we get our equation of line. That's pretty awesome. We just found the one line in the world that's going to intersect this curve going through space at that exact point and have the exact same instantaneous velocity at that point. Pretty awesome. Should fans feel okay with it? Tell you what I want to do, since we have about 5 minutes before I want to stop, and then we're going to go on to. You heard that too, right?
Yeah.
Okay, good. When you don't hear that and I do, that's when we got a problem. Do you want to try one on your own?
Yes.
You're like, no, too bad. You can do it. The answer's always yes for that, by the way. I want you to try one. I want to see if you can do it. So what I'm going to do is put one up on the board. I'm going to give you about 2 minutes. We're going to go through it pretty quickly. It's not too bad once you handle this. You know what you're doing. It's not too bad. You just got to get this stuff organized in your minds. Okay, so try that with this. By the way, a lot of people take what I say over here, the whole unit tangent thing, and try to apply it immediately. I want you to know something. This unit tangent stuff is important. We're going to use it later. But did we have to use a unit tangent here? No. Any tangent will work. Any tangent vector. If you wanted to have multiplied all this through and taken the fraction out of it, you could have done that. It's okay. You can do stuff like that. So it's all I want is the direction that's headed. That's what we're doing. Oh, don't scoff. It's not that bad. I'm not joking. It's not that bad. It's really not. Here's what I want. I want the same question. You better believe that this would be a test question for me, for sure. Find the equation of the tangent line to that vector function at that point, at that time, at that value of t. Do you all understand the question? 2 things you need. A point and a vector. Which one do you find first? Find the point of tangency. Then how do you find the tangent vector? Find derivative, plug in said value that you get the point from, and then you got a line. So I'm going to give you those 2 minutes. What I'm going to be doing, about every 10 seconds, I'm going to put a new step up on the board. You better beat me to the steps. Oh, do I want to use that notation? Yeah. Did you find your point of tangency? Did you get 1, 0, 0? You plug in 0 here, you get 1 and 1, but you get 0, you get 0. Yeah, tan inverse, I know it's fuzzy, but we get it. We actually get a lot in here. So I'm trying to teach you as I teach you, okay? Reviewing as I teach you. Tan inverse of 0 is 0 because, sine inverse of 0 is 0 because sine of 0 gives you 0. Also, we can use this, the derivative of the x component with respect to t. We did this one pretty much earlier. It's very similar. By the way, you guys get a note card, right? If you don't know what the derivative of sine inverse is, put on the note card. That's not a worked out example. That's something you can put on there. That's on a table, okay? So that's not what I'm concerned about. So if you don't know this, I mean, it's on my notes. I would put that on a note card for sure. So derivative of sine inverse is this. Also, please listen, when we get to integrals in about 10 minutes, we're not going to be doing trig sub on this stuff. We're going to use our tables. We're going to be smart about it. Go, hey, the integral of anything looks like this, sine inverse, done. That makes things a lot faster. Okay, we're not in the business of manually doing everything anymore. That's not what we're doing. I know a lot of you are copying, and that's fine. I know I'm moving kind of quick on this one. Are you able to do at least this, the point of tangency? Are you able to get the derivatives down to create for yourself this tangent vector? Show of hands if you are. What's your next order of business? Plug what in?
0.
For this. Because if this is the formula for the tangent vector at any point, I want it at a specific point. What point? That point. What gave me that point? That value. Find the tangent vector at that value. So we're gonna do it down here. We're almost done. If we plug in the 0, the reason why we sometimes organize these like this is because it makes a lot of our work easier. So for instance, if I plug in 0 here, I know that's 1, I know that's 0. So this whole thing is 1. E to the 0 is also 1. I get negative 1 times 1, that's negative 1. Same thing happens here. I get 0, I get 1. 1 minus 0 is 1. E to the 0 is also 1. 1 times 1 is 1. Even though it looks nasty, it doesn't have to be hard. It just looks better. What's t going to again?
0.
So this is also how much?
1.
Now, even though this all sucked, and I wanted to challenge you and give you something that you can see and you can do, but it's a little challenging. Even though this kind of sucked to do, what 2 things you need for a line? I know I'm being redundant, but what 2 things you need for a line?
Point.
Do you have a point?
Yes.
And
Direction vector.
do we have a direction vector?
Yes.
As long as you have your point and your direction vector at that point, I want you to make the equation of your mind. Go ahead and do that now. X value 1 minus 1t. Y value 0 plus 1t. Z value 0 plus 1t. This right here is their parametric expression for the tangent line to that curve, which I have no idea what that looks like, at that specific value t at that point. Is it clear for you? See, this was a pretty big idea, right? Because we just went through like the Calc 1 version of finding the equation of a tangent line to any point of any curve. And we just made it through that. Have I explained it well enough you guys understand? Can you do that? Then I'm happy. I'm happy. We'll take our little break here. We'll come back. We'll talk about integrals. It's really confusing me. I'm going to record that, by the way. It's going to be up there. I'm going to do it. Integrals, we're going to crush them. Integrals are done they're anti-derivatives is what they are. So they're done exactly the same way as derivatives. You do them piece by piece, undo derivative piece by piece. So they work just like any other integral you've ever seen. As long as you have the same variables here that you are integrating with respect to, do them the same way, piece by piece. Since we can separate integrals by distance subtraction, we can integrate each term individually. So even evaluating integrals works the same. So what would that be when you integrate that, please? 1/2 t squared I. That's the only thing, right, is that we have i's, j's, and k's. Please don't forget the i's, j's, and k's. What happens occasionally, not all the time, is people lose the i's, j's, and k's, and then when they evaluate, listen, when they evaluate, they get one scalar function, not vector function. And we need these to be vectors still. They have i's, j's, and k's. We are going to get an actual vector I, j, k. So I, and the next one, please.
130 J.
And
1/4
are we done?
No. It's evaluated.
T equals 1.
Do definite integrals need
No.
plus c?
No.
Do vector integrals of vector functions need plus c at all? We're going to talk about that. We're going to talk about that later, okay? In like a minute. But right now, when you're evaluating integrals, you don't do plus c. What we do, I know, we plug in 0 to 1. The thing is, if you want to be smart about it, plug them each into each term individually. Don't plug in 1, 1, 1, and then 0, 0, 0, because then you have to recollect terms. So because we can separate by addition subtraction, plug in 1 minus 0 here, plug in 1 minus 0 here, plug in 1 minus 0 here. Does that make sense? I'll say that again. Don't plug in 1 and get one vector, and then plug in whatever this is and get another vector, because then you have to recollect i's, j's, and k's. So what you should do is take this individual thing as a function, this as a function, this as a function, plug in 1 minus 0, square it with the I. That works just as well, it works faster. So you don't have to recollect your i's, your j's, and your k's. Plus 1/3, 1 minus 0 to the third, j. Plus 1/4, 1 minus 0 to the fourth. Now, of course, I gave you really nice numbers, but any two numbers like that are going to work just fine. And now if you're okay with that one. Okay. What's he give us?
1/2 I.
And that's the point I want you to see, is that this thing is still a vector. Now we talk about what these integrals actually mean a little bit later. We start getting interpretations of integration later. Right now, we can't really talk about area under a curve yet. But if you think about what integrals are area under curve, correct? So this has something to do with that. But when we start talking about area under a curve, and this is a vector function in a curve, we're going to start talking about line integrals and start talking about what that actually means. What is the area under curve? What is the length of a line through space? What is that stuff? Right now, I know it seems kind of like, it's almost calculus 2e. 2e? Whatever. We're going to just do integration for the sake of integration. Even though that kind of sucks, we're going to leave the interpretation for a little bit later. Okay, that's how we have to handle it for now. I come back later and we start really talking about what do these integrals mean? What is the area under a space curve? What's that even mean? What is a double integral? What's that mean? But we don't get it for a couple chapters. You guys understand? So right now we're just practicing integration, seeing how it works. That's really the idea. Oh yeah, next one. Cool. Just like we do derivatives of vector functions, when you do derivatives, you're free to do the derivative of each piece individually, correct?
Yes.
Same thing with integrals. Because these are three different pieces, listen, you're going to have several different techniques going on with this thing. You can't use the same technique for all of this stuff. Easy ones? Yeah, okay, do them in your head. But when you get stuff like, hey, t cosine t, please take the time to just write this out and do it separately. So the first thing I would do is do that integral. And at the very end, make sure I have an I, because that's what's going to happen here. You guys all right with what I'm talking about? Oh, how do you do that?
Integration by parts.
That's it by parts. So U sub don't work. Is U sub going to work here?
Yes.
Yeah, just fine. How about there? U sub should be your go-to guy. Watch your Calc 2 videos if you don't remember it, but U sub first, then we try things like by parts, trig sub, integrals by trig integrals, and then we start doing other crazy stuff. But for sure, we're going to do a lot of U sub and a lot of by parts. Can you do that? Remember, we're reviewing and I'm teaching as I'm teaching it here. So what would your U be? U would be what now? T. And the V would be the integral of whatever's left over. If you didn't have me for Calc 2, this is how I do it. U is the piece you can derive easily, and V is the integral of whatever you can actually integrate. So I want the U to be a piece where the derivative gets nicer, not worser, okay? And the rest of it should just be possible to integrate. I wouldn't pick this for my U, because even though I can integrate this, it gets worse, and the derivative of this does not get better. So the derivative of this is nice. It's just dt. And in my opinion, is the best way to do integration by parts. Whatever your U is, cover it up. V equals the entire thing that you see. V is the integral of cosine t dt. I don't do dv because you can get it the same way this way. It's nicer. If you do dv equals cosine t dt, you have to integrate both sides to even get the v. So why not just do that anyway? So v equals integral of cosine t, which is in our case, here's where they come in. Sign or negative sign.
Sign.
If you put negative sign on the test, are you going to be very happy with yourself when you get that test back? I'm begging you, please. I don't want to have to burn your test to warm my house. All right? My heater goes out from time to time. I will do it. I will. I lost it. I don't even know. I wouldn't do that to you. But seriously, get your signs right. For real. Okay, well, it's in this integral, therefore, is u times v minus the integral of v du, which du is dt. That's our formula here. And we get t sine t minus,
Plus.
what's the integral of sine t?
Negative.
Negative, so minus the negative. Now here comes the first little question. Here's the first question. Whenever you do an integral and it's not a definite integral, what do you always put at the end of that?
Constant integration.
You do a plus c. That's right. But now check this out, because you do have to have that. But we also have 3 parts. So we're going to have 3 plus c's. We're going to call that one C1. This is the onlyest time we're ever going to do it, and I'll prove to you why. This is why we're doing it. I get to prove it, okay? There's one thing we're forgetting. What component did this come from? The I, the J, or the K? Put the I. So this was number 1. Here's number 2. Tell you what, for the sake of time, would you mind if I just gave you the answers here? I really don't want to waste time. Yes?
If we didn't integrate those individually, would we have to have C1, C2, and C3?
We are going to have C1, C2, C3, but I'm going to show you what to do with it, okay?
Okay.
You better have C3, or I'll be PO'd. I'm going to get hate mail for that one. That was just horrible. I'm going to ask the question again. Do you know how to do this freaking integral right here?
Yeah.
What does that? Do your use of on your own, okay? Or use calculator, do your use of. I don't care. What you get out of this thing is -1/2 cosine t squared. But wait, this is another integral. Does this plus c have to be the same as that plus c? No. And then we got the third piece. You know, there's an option right here. Me personally, I like taking the sign with my integrals. You don't have to, but I like doing that. So when I have positive, I leave it positive. When I have plus, I leave it positive. When I have minus, I bring that down. That way when I put it back, I don't forget about the sign. It's very easy to forget about that sign. Are you getting me what I'm talking about? So I would consider this to be this integral. So I'm gonna put this here and make sure I have that negative floating right in front. That way when I put this thing back together, I don't have to worry about my signs. Do you have to do it that way? No. It's just, I think it's good practice. Head nod if you're okay on that one. Now, how about this one? How do you do that? How do you do this one? Do you remember?
LM?
Series. Please pray I don't give that one. If I give you that one, it's a typo, okay? So this one is, yeah, that's nasty. But you did it in Calc 2. Watch the video. It's on there. That one's another u sub. What would your u be? What is that one? Yeah, the derivative is 2t, so we should have a 2 floating out there somewhere. Our answer here is negative because of that negative. 1/2 e to the, what is it, t squared? But then this plus c doesn't have to be the same as these ones either. Now we're going to talk about what all that means. But I want to know right now, do you feel, I know I only did the by parts because that's the one people normally struggle with. Are you guys okay on the u sub and the u sub? Show of hands if you already feel really good about that. So, we did our integral. Here's our integral. Our integral says we have this whole thing I, this whole thing j, minus this whole thing k. Okay, so, but wait a second, I want you to look at this. I can separate components of my vectors, which means that I can really think about this I plus C1I. I can separate that. Do you guys catch what I'm talking about? I can do the same thing here. I can pull off that C2J. I can do the same thing here. I can pull off that plus C3. Oops. Okay. Now here's the deal. The only reason I'm doing it is to prove it to you one time. If I combine these three things, what I'm going to get at the very end of this is this. I'll get my I component minus my j component minus my k component. And watch carefully, because you're never ever going to do this C1, C2, C3 thing again, but I need to prove it to you why we don't do that. At the very end, I've got this C1i plus C2j plus C3k. True or false? That is a vector. This one thing right here, true or false, that is a vector. True or false, that's a constant and a constant and a constant. Yeah. This right here, when we wrap this all up, creates for us a constant vector. So when we're doing integrals, we don't really show the C1, C2, C3. We say that this whole piece of junk is just a constant vector. That's the plus c we get in integrals, but I needed to show you that it's not plus c a number. It's plus c a vector. It's just a constant vector. That's what I need you to get. Show of hands if you see what I'm talking about. So next time you go through it, listen, the way we actually do it, don't worry about the plus c's here. Do the integral like you normally would, all the way down to the very end. Just put plus c, but understand that that plus c is just a constant vector there. Are you clear on this? For real? Can we go through and do a couple other ones here real quick? Do you know the answer to that question? You're learning. You're learning. Is this stuff the most entertaining stuff you've ever seen in your life? That answer is all, no, okay, you don't have to lie. You don't have to lie. I think it is, but that's why I have a master's degree in math, man, because I love it. I didn't always, though. I used to hate this stuff. I really did. But then, for some reason, I went crazy. Hey, this is a fun one. That'll wake you up. That's a good one. I'm going to make a suggestion to you right now. And so we're going to do this one from start to finish. I'll show you exactly how I would expect it on a test. These should probably be some of the easier ones that we do because I know it's just integration, but you've handled integration last semester. You know all about it. Everything there is to know about the techniques of integration, you covered in Calculus 2. Now, the method on how you do it, I'm not even joking. As little work as possible. That sounds crazy coming from a teacher. As little work as possible. What that means is, if you have something that's in an integration table, use it. If you got something that's a U sub, of course you do that. But if it's integration table, it's something that you know, man, use it. For instance, I know that at least half of you out there can tell me what the integral of 1 over 1 plus t squared is. I know that you know that. What is it?
Tan inverse.
Tan inverse. Done. You remembered it. I'm so proud of you. So this integral starts off with, I know that's tan inverse of t. Real quick, do I need the plus c? Yes, no. No, we wait to the very end because we know that whatever we put here for our I, it's going to be wrapped up in this constant vector that I'm going to add plus c at the very end. I do need the I here, though. Okay, how about this one? Is this an integration table? No, not really. But can you do a U sub with it?
Yes.
Okay, so we're going to do a U sub there in just a second. How about, that's a little more obscure, but how about that one?
Sine inverse.
That's sine inverse. In fact, I gave you this earlier doing the derivatives so that when we got here, you go, oh yeah, hey, that's that thing. So this part goes to tan inverse. This part goes to minus sine inverse. And this part is U sub. Can you please do the U sub on your own and then put this thing back together? What would you pick for the u? Would you pick t squared, 2t squared, 1 plus t squared? What would you pick? What do you think? For u subs, you always pick the inside of something. You pick the nastiest thing you can, such that the derivative of said nasty thing is somewhere in your integral. The more you can pick, the better. What would you pick? Pick the whole thing. The whole thing. Because the derivative of 1 is
0.
and you can do the ln thing, okay? Pick as much as possible with the u sub such that the derivative is still there. The u sub is the reverse of the chain rule, all right? So it's a composition idea. Pick as much as possible. So our u would be 1 plus 2t squared. du equals 4t dt. I have done this two different ways. A lot of times what I'll do is I'll solve for the dt, divide by 4t. Or you can solve for the t part of it. That's fine also. So what I mean is du over 4 and solve it for t dt. This piece is this with that dt. That dt. That's fine to do it that way. I don't care. I know when I teach this for the very first time, I teach it solve for dt. That way you're seeing this canceling out of that t. Either way works. I don't care at this point. What I do need to see is that you see this integral changes to this integral. Here's our t dt, here's our t dt. We get 1 over u du over 4. That's what I need you to get ultimately, no matter what way you do it. That's what I need to see. And now if you're okay with that one. And then we keep on going. Y'all should know what the integral of 1 over u is, like, by heart.
Absolute value.
Oh, love that. So 1/4 ln absolute value of u. But what's u?
1 plus 2t squared.
Question. Left-siders only. Do I need the absolute value?
Not a,
Why do I not need it here?
because t is
Negative.
negative.
Use a table, tan inverse. Use a table, sine inverse. Use the easiest thing possible, u sub, with as much as you can. You do need to know how to do u sub to be successful in calculus. Sorry, there's no way around that. We do a u sub, don't need absolute value, and now we say that our integral, all said and done, is tan inverse plus 1/4 ln, no absolute value, bunch of junk in here, minus sine inverse. Oh, I forgot something. It happens a lot. It happens a lot. I do it all the time too. What did I forget right now? These are still vectors. And then you're done. If you forget the plus C on my test, you're gonna see a C, all right? At most. Don't forget the plus C's, all right? They mean something. They mean a constant
Integration.
vector of integration in this case. So all that C1, C2, C3 gets wrapped up in that plus C. That's how you integrate. Have I made it clear for you? Okay, now, the last two things, I love the last two things. In differential equations, you go, what? That's a dirty word. I know, it starts with a D and it's a dirty word, diffie-q. We can often, in the most basic form, we get these things called initial value problems. Initial value problems are how we get rid of the plus C. In order to get rid of the plus C, you have to have some statement that says your original function has, you have an input and an output, and you can get rid of that plus C. Until you do that, you're dealing with a family of vector functions right now, a family of curves, just like in Calc 1. Integrals give you families of curves. Integrals give you families of vector functions, space curves. If I want to get listen, please listen. I hope that you're focused here. I know we only have 15 more minutes, but if you want to get a specific curve, you need to tell a specific point that you're going through. So this is a family of curves plus constants. That means they're shifted, right? They're shifted all around. So I say, hey, here's this whole family of curves traveling through space, and I go, now, I want the one of them that goes through this point. That eliminates all but one of those things. So to get a specific vector function from integrals, to get rid of the plus c, in other words, you need an initial value. I'm going to show you how to deal with that. We're going to do 2 examples. We're going to end our day with it. They're not super hard. It's just integration. You just need to know what to do at the very end of it. Are you guys with me? You're just going to nod your head, so I just keep on going, huh? No, Leonard, we're not doing that. No, Mr. the Leonard, you just told me to nod my head at everything. Uh-huh.
Seriously?
You know, personally, this whole integration stuff for me doesn't make a whole lot of sense. Just doing ad nauseum integrals until we start putting like a face on it. This puts a face on it. Here's what this says. What is this? What is that? It's a tangent. It's an instantaneous rate of change of a particle, right? So suppose we have this function that gives us the velocity of a particle at any point. Furthermore, suppose that we know that when it starts at the very moment of time that it's headed that way. Can you tell me the position of that particle? Well, that's what these integrals do for us. That makes it more real life. If you've got a velocity function, so giving us the velocity at any given time of this particle, and I know that particle starts right here at time 0, it's headed in this direction. If I know those two things, then I can create a vector function for that particle. I can give it a space curve and say this is where that particle is actually traveling. That at least gives this a little bit more flesh on the bones, rather than just doing countless integrals. We get to do something. We get to create a position function for this. Does that make sense to you? A space curve of this particle traveling. Well, how do we do it? What undoes derivatives? Antiderivatives. Yeah. So I want us to find the vector function from that velocity function, from that first derivative. In order to do that, man, just take an integral. An integral is going to give us a function from a derivative. Can you go ahead and do that right now for me? Show me everything you need. Oh, wait, hang on. Constants go to 0, don't they? Where do constants go to 0? Are we deriving?
No.
Don't drink and derive. Don't let your constant go to 0. Gotta do. Yeah. 2. Then? Love it. Quick as possible. Just do it efficiently. That's fine. Then what?
Minus 2. JK.
I'm not just JKing. Yeah. You need the JK. I know, it's so stupid. I'm sorry. I can't help it. I'm tired, haven't had no candy, so. I know that. It's my fault. It's your fault. There's like 50 of you. There's like one of me. Who's supposed to bring candy? You. You guys know how to integrate, yeah? Do you understand that when I integrate something that's a derivative, I get at least the family of curves that when I take a derivative gives me this it's derivative. It's an antiderivative for a reason. Well, we're forgetting something major. What is it? We need this constant vector that's at the end. That constant, that's important. Now, how we put these two ideas together, this is why we needed the initial value to eliminate the plus c. So track with me for a second. If I give you a tangent vector, or a tangent vector function, I can integrate to find the original vector function. If I give you an initial value, here's what this says. Here's what this says. When you plug in 0 to your vector function, you must get out I plus k. Do you get me? When I plug in 0 to my vector function, which I have, please watch carefully, this is where people get really lost. When I plug in 0 to this vector function that you just found, 0i, oi, plus 0, he went to jail, minus 0k plus c. That's what I get when I plug in 0 to my original vector function. Does that make sense to you? But there's more. We also know that it has to equal I plus k. This is what my initial condition said. So the way this works, do your antiderivative. Yeah, get your family of space curves. Plug in the initial value that it says. This says when you plug in 0 plus c, you have to get it. This must be equal to I plus k. If this equals r of 0, which it does, and this equals r of 0, which it does, transitive property, they got to be equal to each other. Does that make sense to you? Solve for c. Now this is really nice because everything's 0. That's pretty convenient. But solve for c, and we get that c equals the vector. Look at that. Hey, is c a vector?
Yes.
Is c a constant vector? It's a specific constant vector. We have the plus c now. And just like any other time that you do initial value problems, if we take that plus c and substitute it here for our family of space curves, it no longer gives us a family. It gives us a specific space curve. So our vector function now becomes 2ti plus 2 square root of tj minus 2t cubed k plus what? Plus c. C. I plus k. Did you follow that one? There's only one more thing to do. What do you think? What would you do? If I give you this, would you leave it like that? I wouldn't leave it like that. Why wouldn't I leave it like that?
You can combine it.
Because you have these components that are like components. You got an I here, you got an I here. Just combine them. Just combine them. Oops. So I know that this is 2ti. Well, this is how many i's over here? So if I combine these, factor the I get 2t plus 1 I plus how many? What do I do with the j's? Do I have to do anything to the j's? Then what? I'll give you a hint. I'll give you a hint. Keep that sign with this term. Always put a plus. It'll help you out tremendously. Because if you put, please watch carefully. Don't write this down. Just watch. If you put minus 2t cubed in parentheses, you have to change it to a minus 1. Do you guys see that? You can do that if you wish, but oftentimes it's easier to just go, you know what, let's call it a plus. That way all our signs stay the same, and we don't have to worry about it. Does that make sense to you? Group it like that, and then you don't worry about it. Just put pluses all the time. That's fine. If you get 2 minuses, yeah, maybe factor up a negative. That's okay. But just watch, man, goodness, watch your signs. Watch your signs. Did you catch the idea?
Yes.
I want to do one more. I really do. I want to do 2 iterations. It's going to be crazy awesome. Awesome fun, maybe even? Did you get the idea, though? Mm-hmm. If I give you a derivative, integrals don't do that. Solve it. Initial value just says, hey, plug it in. Solve for c, and then you got the actual vector function. Listen, we're going to move fast here because I don't want to take up a whole lot more time, all right? We're going to move fast. But I want to show you how in-depth we can get. For instance, you've seen this in Calc 1. You've seen that we can go from acceleration to actual position. And we're going to do something very much like that right now. So let's say that I go... I go that deep with my derivatives. Here's my question. In order to get the actual vector function, no derivatives, in order to get that, I've got to give you some pieces of information. What must I give you in order for you to solve for the original vector function with 0 plus c? So what do I got to give you?
Initial point.
I got to give you...
Point of k.
Well,
What happens when I do the first integral? What do I get? I get a derivative. I get the first derivative, which means I get velocity. In order to get rid of that plus c, I need an initial velocity, or at least something to do with velocity. Does that make sense? Now that's enough to get us to the first derivative. But how do I get down to the position function? I'm also going to need an initial position. I'm going to need at least a point somewhere on that curve. So no matter however many derivatives I give you, that's how many initial conditions, we'll call them, that you need. If I give you a first derivative, one initial condition. If I give you a second derivative, you need two. You need to get back to the original. So I'll also give you that the initial condition of our position function, or just vector function, is this. Do you guys understand the process? I'm not going to be talking a whole lot. Well, I'll probably talk a whole lot, but I'm not going to be asking for your help. I really just want to run through it one time to give you the feel for this stuff, and then we're going to call it a night. Make sense? So here we go. How we get rid of any sort of derivative is with an integral. So if I have a second derivative, I can integrate and it raises me up a derivative, basically. If I have a second derivative and I integrate, I get a first derivative. However, when we do that, oh man, that's not my T's. When we do that, whenever we integrate some sort of indefinite integral, we get a plus c floating around here. Every time we get a plus c, we got to have an initial condition to get rid of it, which is why if we have two integrals to do, we need two initial conditions to get rid of those two plus c's that we're ultimately going to get. Quick hit now if you're okay with that so far. Are you guys doing it as I'm doing it? Mm-hmm. Awesome. So this is the first derivative of our vector function. I have something that relates to that. What I know is that if I plug in 0, I have to get I plus k. When I plug in 0 to my first derivative, okay, well, hey, this is 0. Tangent of 0, still 0. Oh, wait, e to the 0, how much is that? 1. Plus c. Do you all see where this is coming from? When I plug in 0, I plugged in 0. But I know it has to be equal to I plus k. That's a must. It's got to be equal to I plus k based on this initial condition, initial velocity, if you will, of this vector function. Show of hands feel okay with that one. Okay, cool. What do you do next?
solve for C.
If we solve for c, be something pretty nice. 0, 0, that's great. I love that. If I subtract k, I get I. That's it. Let's go ahead and let's rewrite this. Remember, this c becomes just I. So that becomes just I. Do you ever leave that I hanging out? You actually you can, but it's not a good idea. Just put it in with this part, this component of the vector function. And we don't need a plus c anymore. We took care of that plus c with the initial condition. So, hey, second derivative, yeah. Integral gives me first derivative. No problem. Use my initial condition for whatever derivative you currently have, or whatever function you currently have. Plug in the value. No problem. Plug it in exactly right here. Keep it exactly the same. It's just set it equal to whatever that initial condition says. Solve for your c, and then put it back into your problem. Organize your components, and then you're good. That's halfway there. We're almost done. Now I got one more thing to do. What's the next thing I got to do? The vector function itself is the integral of the first derivative. As I'm erasing, maybe you can be doing. Why don't you try to do those integrals? At least the first one and the third one. If I integrate here, that's our 5/2, so 2/3. Should be 2/3 times 2/5. Plus t I. You guys see where the 2/3 comes from, where the 2/5 comes from, where the 5/2 come from, and then plus 1, we're integrating here so we get our t. Plus, man, the tan t, that's in your table. Okay, it's in the integration table. Also, if you don't know that, you do sine over cosine. You do a u sub on cosine. You're going to get a negative because you have the derivative of cosine's negative sine. You're going to have an ln. And you're going to have an absolute value of cosine. So it's negative ln absolute value of cosine, or ln absolute value of secant. Because that negative moves up, negative exponent reverses 1 over cosine, and that becomes secant. Either way works, it's fine, I don't really care. Me personally, because I like the u sub version of it, I know this becomes minus ln absolute value cosine. If you look in the integration table, it probably has ln absolute value secant, because that negative acts as an exponent, gives you the reciprocal. That 1 over cosine gives you secant. They're both right. Tell you what, the hardest one, I gotcha. But then we get another c. If you really want to be accurate with it, you call this one c1. You call that one c2. Does it really matter? Not really, because you're dealing with each c as you're going. Does that make sense? So your c is now, you have no more constant. It's in the problem. Just call it c and you'll be fine. If it's confusing, you call it c1 and c2. Yeah, we do it here if you really want to. c1, c1, c2, no big deal. Here's the whole main point. We just integrated. We have this nice expression here. The only thing we have to realize is that in order to get rid of c2, we have an initial condition. This says, hey, if you got your vector function, which we do, and you plug in 0, which we're about to do, you have to get this. You have to get it. So I'm going to plug in my 0. Well, if I plug in 0, that's gone. Oy. What's ln of, cosine of 0? 1. What's ln of 1?
0.
0. Plug in 0 here, we get 1k plus c2. Are you following what I'm talking about? If I can get you to say what this is equal to and you get it right, I'm going to be really happy. What's this have to be equal to? Beautiful thing. Now, what did you say? That's what this says. It says if you plug in 0 to your vector function, which I did, whatever your vector function says, has to be equal to this nonsense right here. It's gotta be. And then you solve for C. So let's solve for C, or C2 in this case. We get 2i plus j. Keep going. 0 or minus 2? This is the piece that you're going to use to get rid of that C2. Can you do it? Tell me what the first piece would be.
415 t divided by plus t plus 2.
All of that, I. Somebody else, I want the next one. Someone else over here, what's the next one? How would you write it? Would you write plus or minus? I'd write the plus. The reason why I would do that is to keep this sign with it. That's nice. And you can just put the 1j first minus ln absolute value cosine t. Which, of course, tells you that, you know, if you're checking answers, you might get slightly different formatting. That's okay. It's the same stuff. And we've managed to build a precise vector function, not a family of curves, a precise vector function that has this initial condition. So basically travels through that vector, has that vector on it, has that vector for the velocity, and has this thing as its acceleration curve. That's pretty neat. Did you understand what we were talking about today? Did today make sense for you? We've covered a lot of stuff. This right here, on a test, I'm stopping you after the first iteration. Okay, this takes too long for me to put it on a test and have you do both. I just want to show you that it's possible, and it's really, really good practice for us. You sure you have no questions or anything else? All right.